In this lesson video, we're going to be taking a look at characteristics of quadratic functions or characteristics of quadratics. We've been talking about how to graph them if we're given the equations in either of these forms. We've also talked about how to write these equations if we're given a table or a graph. We're going to kind of re-examine what the different pieces are about quadratics. So some of this will be a review of what we've been talking about. Other parts will be a little bit new. And so you'll remember that there's two different forms of writing quadratic equations. We've got vertex form, which looks like this. This is kind of the newer form. And then the general, or what we call standard form, which is this. And we've used both of those, but we can write any equation in either form, and that could represent the same parabola when graphed. Quadratic functions, when we graph them, do give us these U-shaped curves. Okay? And so they give us these kind of graphs as long as a does not equal 0. Because if a does equal 0, let's just take standard form. Okay, that would turn this into 0x squared plus bx plus c. Well, 0 times x squared actually just cancels that out. So it turns our equation into y equals bx plus c. This would be a line graph or a linear function. And so that's why a can't equal 0, is because it would make it linear. So let's go ahead and take a look at how these different characteristics are compared with the two different forms. Some of these characteristics, like vertex, axis of symmetry, and then the y-intercept, really are a little bit different or found a little bit different depending on which form we are using. So let's start with vertex. All right, for standard form, you'll remember that we found the vertex by using, I'll zoom in for you, x equals negative b over 2a. And then to actually find the rest of the vertex, you would just plug that into the equation for x and find what y is. But if it's in vertex form already, remember, we've got this h and k coming directly from the vertex form. Remember our saying that h lies and k tells the truth. That just means we want the opposite of whatever the h is here and the exact value of k to find your vertex. And so then we go to axis of symmetry. Now, again, from standard form, that's actually what we started with to find our vertex. So that's your axis of symmetry. But in vertex form, it's just x equals whatever h is. And then lastly, or thirdly, the y-intercept is just really when I plug in 0 for x. Okay, it's anytime x is 0, if I plug that in, it ends up being just this last number c. Well, for vertex form, we do have to actually plug in 0 for x into this formula and get a value for k. Okay, so these two different forms of quadratics provide information about the function's graph in different ways. But these last two ideas really are the same no matter which form you're in. The first is called a point symmetric to the y-intercept. Well, here's what that really means. Okay, so if I've got my y-axis and my x-axis like this, okay, and I've got a parabola maybe that goes like this, you would have an axis of symmetry there. Well, this ends up being the y-intercept because it's where that curve crosses the y-axis. We're always going to have another point directly across called a point symmetric to the y-intercept. Okay, a point symmetric to the y-intercept. All right, and so we do that just by reflecting this point across the axis of symmetry. It's really just counting. So we'll look at that example here in a little bit. All right, and then we also have what we call the X-intercepts, and those again are really the same no matter which form we're using. Those are called our zeros, okay? We've talked about finding those before. That's where we cross the x-axis, okay? That's when y equals 0. And so we replace both of these with 0 to find that. All right, so we're going to actually try and, given an equation, find these pieces of information. We're going to go through with a standard form and then a vertex form. Now, you will notice that I talk about using the calculator's command or a function in the calculator. We'll look at that in class. So don't worry about that right now. I will show you how to do that in class. All right, so let's go through and take a look at this equation. To find the vertex, we actually find our axis of symmetry first. All right, we're actually going to do x equals negative b over 2a, in which case we're going to do the opposite of our b value. So if b is negative 2, negative b would be positive 2 over 2 times, there is no number in front of x squared, so a is 1, which becomes 2 over 2. So our axis of symmetry is x equals positive 1, because 2 over 2 is 1. And so to find our vertex now, we're going to go to our equation, and we're going to plug 1 in for the x in both places. So 1 squared minus 2 parentheses 1 minus 3. 1 squared is 1. Minus 2 times 1 is minus 2, and then minus 3. And so 1 minus 2 minus 3 ends up giving us negative 4. So our ordered pair for our vertex is the point 1, negative 4. Okay, and that's where our vertex would be. Now the y-intercept, again, you'll remember that just means I take my 0 and plug it in for x. Well, in standard form, if x squared is 0 squared, and negative 2 times 0 gives us 0, those two really just cancel out, and we're left with negative 3. So the y-intercept is 0, comma, negative 3. 0, comma, whatever that c number is. Remember, we're using a x squared plus bx plus c. And now to find a point symmetric to the y-intercept, we're going to kind of imagine where this is on the graph. Okay? Okay, so my axis of symmetry goes through my x value at 1, but then my y-intercept is at 0, negative 3. So it's down there. Well, notice that this point, my y-intercept, is only 1 away from the axis of symmetry. I'm going to look at their x values. 1 is only 1 away from 0. So my point symmetric on the other side of the axis of symmetry is only 1 away from the axis of symmetry on the other side. Okay, so if this is 0 and this is 1, this has to be 2. The y values don't change, so my y value is still negative 3. But now my x value is over here at 2. Okay, and then to find my x-intercepts, I'm looking for the zeros of this function. Now, the best way to do this, we can use our calculator, but really the best way to do this is either to try and factor it or use the quadratic formula. And in this case, this does factor. We can actually use our diamond method for factoring. The top number is negative 3. The bottom number is negative 2. The factors of negative 3 that add up to negative 2 are just negative 3 and 1. When I add them, they equal negative 3. When I multiply them, they equal negative 3. When I add them, they equal negative 2. So that tells me I can factor this into x minus 3, parentheses x plus 1. But then you'll remember, whenever we solve this to find the zeros, we actually want the opposites of these numbers. So our x-intercepts, or the zeros, are negative 1 and positive 3. Okay? So let's try and do the same thing, but with this equation written in vertex form. All right, for the vertex, that's easier for us to find this time. Okay, our vertex is just hk, but remember, h lies, k tells the truth. So our vertex is positive 1, comma, negative 4. And the axis of symmetry is just x equals that h number. So it's still this. You'll notice there's the same vertex, same axis of symmetry. These are actually the same parabola, just written in two different forms. So for the y-intercept, I would actually have to plug in 0 here. Okay, I'll come out here where I've got a little room. If I plug in 0 for x, that's 0 minus 1 squared minus 4. 0 minus 1 is negative 1 squared. We do exponents before we subtract. Negative 1 squared gives us positive 1. 1 minus 4 is again negative 3. So again, you do get the same y-intercept Okay, this works out the same way. 2, -3 ends up being the same point symmetric to the y-intercept, and we'd have the same zeros. Okay, to find these zeros, we would do this a little bit differently. We will talk about that in class. You can ignore my little marks here. All right, but that's how we find these characteristics given those equations.